Okay, so after these, the introduction to how we set up the challenge, I'm going to give some of the results that we obtained. So this year we had 12 teams participating. It's a pretty complex challenge, so we are actually very happy. People were very interactive. I mean, there were a lot of questions raised and answers. So I think I answered 150 questions in the site. So it's a very interactive process. It's very interesting. So as Julio said, this is the Model 1. And this is how we calculated the score in Model 1. So we calculated two distances, one for the parameters and one for some of the predictions we asked them to do with the parameters. So the score here is just the sum over all the 45 parameters of this model of the log ratio between the predicted parameter and the real parameter. And so we use the log because, of course, parameters are very different, so they can be very small or very high. So this was a way to kind of get rid of the scale. In terms of the proteins, so one of the things that Julio didn't point, but is so we added noise to all these traces. And so in this case, in order to take account of this noise for the scoring, so we asked for the difference between the value of a certain gene at a certain time point, and we compare that to the real value. And then, so basically, we get a square mean difference, and we divide that by the variance. And the variance includes two terms. One that it's constant, and it takes care of the variance induced by the noise that we use the Gillespie algorithm to introduce noise into the proteins. And so there's a constant part that's basically just 0.1 squared. And then there's a part that depends on the value of the parameters, of the protein, of the value of the protein, and that's also squared. So that gave us two distances, and basically at the end the score was just minus the log of p-values calculated with these distances. And so how did we calculate these p-values? So for the parameters, what we did is just a relative distribution under a null hypothesis. So basically what you do is you get the list of all the parameters of the participants, and you generate random participants where you choose randomly one of the parameters from the participants. And so you do this 100,000 times, and so like that you generate a null hypothesis that you see here. And so you can calculate the p-values for each of the participants that you see here. And because this is a distance, so basically if you're to the left, you have a lower distance, so a higher score, and the p-value of the winner was 10 to the minus 3 for the parameters, so a very good approximation. In case of the distances, we basically did the same thing. So the distances actually, what we did is that we perturbed the network, and we asked for a time course prediction of the value of 3 of the proteins. And so we did the same thing. For each time point, we randomly chose one of the values of the participants and used that to generate a null hypothesis. And so in this case, you see that the scores are even better. And so again, this is the distribution of the null hypothesis. And you see that there were very, very good predictions and some that were not that good. The best prediction has a very, very high p-value. So we were very happy about that. So these are the results. So you see here the winner was orange balls. And you see here the other 11 teams anonymized. So you have here the distance for the parameters, the p-value, the distance for the protein prediction, the p-value, and then the overall score. And one of the interesting things that you can see is that the best performer had the best value for the parameters, the lower distance, and also the best value for the protein distance. But this was not the case for everybody. For example, this team here did very well with the parameters. I mean, they were number 2, but they did terribly while predicting the protein perturbation. So we were really shocked by these results, and so we actually contacted the team and we asked them, did you really get the correct perturbations? And they said, yeah. What happened is that we really didn't try to optimize this prediction. So it really, it really matters to try to optimize the predictions in both cases. I mean, there were some cases where you get good parameters and good predictions. So these are the scores. so it's just the participants, the different teams ordered by the score. So you see that we have a very clear winner for Model 1, and we'll hear about how they did it in the following presentation. So the perturbations of this Model 1, here I'll just show them to you. I mean, basically, it's vary KD of this connection, multiply by 10, multiply the RBS by 2, and then multiply the RBS of this gene 5 by 10, and then we asked the time courses for these 3 proteins. And so these are the results given by the participants, so for each of the 3 proteins. In green, you see the actual the solution, and you see that there's some diversity, but actually, all in all, all the participants got the shape correctly, and some of them did really well and are really close from the solution. So as you know, as I've been saying during the election, arithmetics works, but also aggregation works. As you know, one of the things that Nate Silver does is he aggregates the polls from all the different polls that are being done, and he predicts based on that, and he basically got all the correct delegates, except for I think the senator of North Dakota, which we can excuse him for that. So when we do aggregation, again, aggregation basically what we do is we just calculate the mean of the predictions from the participants. And so we take, so for example, here is the score, the distance of the participants. And here are the aggregated teams, where here in the first case we aggregate the protein predictions of the same one is the winner. Here are the 2 first best performers, then the 3, 4, 5, 6, all of them. And what you can see is that the best performer, of course, is much better because he was a clear outlier. He did really well. But when you take the first and the second team, you do best than the second team. The first 3 teams, you do much better than the third team. You can see this is actually logarithmic scale, so you actually do pretty well. And this is also pretty robust. I mean, it could seem that because there's an outlier, the aggregation didn't work that well. But actually, if you look at the predictions, and in blue you get the predictions of the aggregations, you see that aggregating actually works really well if you compare to the solution and if you compare to the diagram I showed you before. So you get a really nice result in terms of the predictions. So for the parameters, we did something similar. So in this case, what you're seeing is a plot of the actual parameters versus the parameters predicted by each of the participants. So each of these lines is a set of parameters. So you see that if you take the Pearson correlation of the best performer, get a very high Pearson correlation between the actual parameters and the parameters submitted. And when we do aggregation in this case, and in this case we did the aggregation using the geometrical mean, you see that, again, aggregating the results gives a very robust result in the predictions of the parameters. OK. So now for Model 2. So Model 2 was, I think, a really nice and interesting kind of twist to the story. And so as we said, as Julia said, we gave this model, and we asked them to try to predict 3 links that were missing. And I'll show you the solution. So here are the links. So you get this negative feedback to gene 1, a positive feedback from gene 11 to itself, to gene 11 and 7, and then a negative feedback from gene 5 to gene 5 and 6. So they knew there were 3 links that they had to find. So how did we do the score? So this is basically just the solution I showed you. So we asked them to send a prediction where they would say, gene 5 negatively regulates gene 5 and gene 6. That you can see it here. This is how it's represented. Gene 7 negatively regulates gene 1, which is what you see here. And then the last one, which is, gene 11 positively regulates gene 11 and 7. So each participant sent a submission like this, and that's what we used for scoring. One of the rules that we used and that we tried to do is, so if you see the complete here diagram, is we wanted them to know that not every connection was possible. We wanted to reduce a bit the universe of connections because, of course, here you can have a lot of different connections. So the rules we used is that and we were trying to help them, is basically that a single link can regulate up to 2 genes, and a gene can have no more than 2 regulators. What it meant is that basically, here you have 1 regulator, so basically you can add 1 more regulator. And in this case, you have 2 regulators already, so you cannot add a link here. In a third case, for example, here you have 2 genes that are on the same operon, so meaning that if a link comes here, it will regulate 2 genes, and that takes care of the first part of this sentence. And so basically, in this case, you can add 2 more links. So that this, try to help the participants, but things are not always clear. And this is how we did the score. So the maximum score is 30, and calculated in the following way. So this is the team that won, it's Team Crux. And basically, if you guessed one of the connections, you get 1 point for the initiation of the connection, 1 point for the sign of the connection, if it's a positive or a negative, and 1 point for where it was connected to. And because you guessed the 3 of them, you actually multiply by 2, and you get a 6. You get 6. And so you have 6 here, plus 6, plus 6, plus 6, plus 6. So that's 30. So the maximum score is 30. We actually had to adapt a little bit because, I really thought that people were going to all solve the challenge. When you start these things, you're really a bit blind. I mean, you don't know how difficult things are. So, I thought that this was just, a nice way of scoring, and then you get zeros. But actually what happened is that, as you will see, things were not so simple. So we added some additional points in the following way, saying, OK, if you guessed one of the connections and the sign, then you get 1 point plus, with the sign, plus 1 point for the connection. So you didn't find the correct connection, but you did find that 1 gene was implied somehow. So you kind of did half of the work. And again, if you know that one of the genes is regulated, then you get 1 more point. And again, here again, you get 2 points because he guessed this connection. So basically, the winner got a score of 12. OK, so in the same way, what I did in this case is that following the rules that I just showed you about who can connect to what, I generated a random set of submissions, and I scored them. So just by following the rules of who can connect to what. And so here you get the normalized histogram of basically a null distribution. And as you see, the best performer had a p-value that was over random, but it was the only team that actually did had a significant score, so higher than 0.05. So these are the scores. So a few teams did pretty well. I mean, they basically, and you'll see in the following analysis what happened. And one of the nice things is that there was a team that decided not to participate in Challenge 2 and sent random submissions. And actually, he got a random score. So actually, it's good. It shows that you could not solve these challenges by sending random submissions. OK, so these are again the scores. You see there's a clear winner, which is Crux, but then there's these middle ones actually are not that far, and it was, but at least we could easily distinguish a winner. OK, so what did people find? So nobody found this link, which was the one that I which is this one, the one here, the smaller one. I don't think it had to do with the size of it, but it was hidden here, and nobody found this gene. So one of the things that I think might have happened, and I haven't talked to all participants, is that this model was different than model 1 because we added some complexities. So if you look in detail, one of the complexities we added is, for example, this gene 3 produces protein 3 that's transformed into protein 4. And a participant asked me, how can a protein be transformed into another protein that doesn't exist? You should go back to your molecular biology books. But actually, I mean, you can think about a lot of things that, hypothetically change a protein to another. You can cut a protein, you can phosphorylate it, you can, So this was a complexity. And the second complexity we added was this gene 5 was regulated in 2 operons, basically. So there were 2 copies of gene 5. And I think that some people interpreted the fact that here gene 5 is regulated by 2 connections, that this gene 5 couldn't receive any more connection because this gene 5 had 2 connections. So I don't know, but it was really surprising that nobody guessed that connection. So this connection was the one that most people found. So the feedback from G7 to G1. And four participants found it. And this connection was found by 2 participants. So can we also aggregate in this case? And so what I did is I counted all the edges that people submitted. So for example, this one, the 11 negatively regulates 1, 8 people guessed this connection, 6 this one, 4 this one, 3, 2, 2, etc. And so if we take just by voting, the 3 best links, which are these 3, you actually have a total score of 12, which is the same as the best performer. So, aggregation also works in this case, which is always nice. Okay, and just to finish up, some of the mistakes or the hard decisions that participants had to make was, this is the correct topology of the network. So gene 11 positively regulates gene 11 and 7, and gene 7 negatively regulates gene 1. But some people actually added that gene 7 positively regulated gene 11 and 7, and that gene 11 negatively regulated gene 1. So, those were the difficult small differences that the participants had to find. Okay, so just as a conclusion, participants had an excellent overall performance while solving model 1, I think. A few additional complexities in model 2 complicated the solution. And aggregation works both for perturbation predictions, parameter, and network topology estimation. So thanks a lot, and thanks to the participants and to the people that made this challenge possible. It's a big collaborative effort, with people everywhere around the world. So it's very nice to come to a nice conclusion. So the IBM team, the EBI team, the SARO lab, so East Coast, UK, West Coast, and then challenge participants a bit everywhere. Thanks a lot. So I guess, yeah, there are questions.
Exactly. Questions about the challenge? Yes.
If I may. So as a naive biologist from the RECOMB part of the conference, sitting in for DREAM, I couldn't help notice 2 interesting things. First of all, you guys are still playing around with microarray data instead of RNA-seq, and you're ignoring non-coding RNAs of all kinds, microRNAs, link RNAs, and so forth. So my first question is, do you think that models are available to overcome this limitation for mammalian systems, or are you developing them, and when? And my second observation is, despite the first limitation, some predictions still worked. There were clearly regulatory events that you were able to detect. So could you explain that success that happened despite the profound RNA limitations?
Do you want to say something? I mean, we are, again, in DREAM, we're very open to any evolution of the challenges, and I think that's how DREAM works. If there's an interesting question of if we can add more knowledge to things, we are pleased to do that. I think that models that quantify, via RNA-seq, for example, perturbations are just starting to be known, but I think it would be a great addition, right? We really, I mean, these are very, toy models, and I think, one of the ideas, if you think about the work of Michael, for example, would be, can we do this with real, synthetic biology circuits? I mean, can we? And the answer is, difficult to have, because as you see, even a small circuit can have all the complexities that kind of Michael was talking about. So this is really kind of a toy model, but I think it really pushes the thinking of, how we model the things in biology and which are the problems that we can find. So, I mean, it's always great to see that in the closest situation to what an experimental situation would be, meaning that, you don't have all the data, you have to choose, you need to, it's almost like a board game, right? That you need a strategy, and people really had strategies, which is very important, no? To see which data to buy, approximated to that. So it's great that they, could find clear solutions for challenge 1, and that they really hit the right nodes on challenge 2.
Can I also add a comment to that? Because I think there are a profound limitation of gene expression data. They're just limitations. And if you take every single moiety that is distinct in a cell, you would have probably 3 million of them. And if each one of them had just 2 states, you would have 2 to 3 million possible states of the cell, which you obviously don't have. And so there's a tremendous amount of redundancy. So even with, you know, whatever, 40% of what is actually measurable, you can still do a pretty good job of measuring, especially in a context that is close to homeostasis or equilibrium in the cell, still do a pretty good job of measuring things. I think some of the additional measurement would be very interesting to identify very dynamical behaviors of the cells, which are maybe not completely detectable from, you know, steady state experiments.
Yeah, I have a question regarding challenge 2. So did you check for each one of the interactions whether they are, what's their effect on the global, it is on, I'll get closer to the mic. So the question is whether looking at specific interactions, they have different effects on the global, on the other genes. And I would assume that some interactions are just easier to detect than others. So did you check whether the fact that one of those interactions was not found was simply because it didn't have profound effect on the rest of the network?
Yeah, so while we were trying to choose the links, I mean, you can answer if you want, but we went through, you know, basically the idea was, let's find links that change the dynamics, but not completely. So things that are kind of intermediate. I mean, it was very heuristical, I mean, right? It's like, we don't want to give something that doesn't change at all, but we don't want something that would kill the behavior, right? I mean, the idea is really, behind this is really, you know, what is the real problem that you confront in biology, right? Well, you're trying to, this is a model, right? We don't know if biology really works like that. I mean, you know, we actually can model it and it works pretty fine. So, but the idea is, you know, how do you decide what is the definition of a circuit? So you are in a situation when things are pretty close, and you know, people really submitted a diverse set of models, right? So this means that there really were a lot of possibilities. Of course, they hit on the correct ones, you know, often, so that's why the consensus, you know, works. But then they were really hitting, you know, all over the place. Maybe I should have done a map of, you know, all the links they added, but it was very, very diverse.
Right. Maybe I wasn't clear enough. Maybe there can be different interactions that can have very similar effects.
Yeah.
So
I think precisely this is a proof of that, right?
Yeah.
These ones
right.
that people submitted. So it's very difficult to distinguish between these cases.
Thank you.
I mean, and a related point even in sub-challenge 1 would be how much does it matter to get close in the parameters to be good to predict well the time series of the variables, right? So, and well, as Pablo showed you, in some cases there's a big discrepancy. So, and it's another thing that, does it matter that you can find exactly the parameters, or does it actually matter that you can predict well?
So in terms of the data that the participant could buy, have you done any investigation of which was more useful and what kind of data were more consistently used by the winning teams, or anything like that?
Yeah, so I mean, not thoroughly, so I mean, we want to publish this, so that's something we will definitely do. But basically people needed to buy, so the data that Julio showed actually is a high definition data of the mRNAs, sorry, the proteins. So people had to choose between low and high definition. We only gave them low definition. So most of the teams always bought the high definition mRNA, let's say, to have a clear idea of the dynamics under that. So that was a key thing. And really then, you know, each team had a different strategy. I mean, it's not, you know, it's not totally clear. I couldn't, you know, give a general rule now, but each one had a kind of clear strategy, right? I mean, it's like when you play Monopoly, right? I mean, what's a good strategy? I don't know. It's the one that wins.
And I guess we'll learn more about that in the next couple of talks.
You know, a similar question, rather than strategy. The best performers, for example, did they exhaust all their credits? And typically everybody exhausts all their credits?
Yeah, I mean, as you saw from the prices, basically you could do 10 experiments, so it's not a lot. It's really, you know, you really have to strategize for it. So, yeah, and actually I think that was a way to see how many people were going to submit. It was, you know, because more than 30 teams started buying credits, but at the end only 12 submitted. So a way of kind of having an idea who was going to submit is, you know, the credits were really low. So, yeah. I guess, yeah, maybe just one last comment is something I found really interesting is that the strategy that people use was really, you know, first try to determine what can be determined. So let's say, you know, if you have an isolated loop, well, in this case, actually, it's not. But I hate doing this. But so for example, you know, these ones are really easy to predict, right? Here, because you have an isolated loop. So they would go for that, right? Let's try to first predict things that seem, you know, more isolated. And then the other thing it was, you know, let's try to predict global parameters like protein degradation. So those were a little bit the things.
Okay. So I think we can move and